Hello and welcome back to this course covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing Layer 2 security and loop prevention. In this lesson, we'll be covering the theory and configuration of Ethernet ring protection switching. Up until now, in this section of the course, we've covered in a lot of detail the theory and configuration of protocols and features for creating and maintaining a loop-free tree topology in our Layer 2 switched networks. This has been focused around Spanning Tree Protocol and its associated features. This is necessary when our networks are built in a hierarchical tree-like topology, where a root bridge and downstream and upstream traffic patterns exist. Tree topologies, though, are very slow to converge. As we saw, STP can take up to 50 seconds, nearly a full 1 minute, to converge into a loop-free topology and be in a steady state of forwarding production traffic. This is largely due to the mathematical and algorithmic complexities involved with ensuring a loop-free topology in a full or partial mesh. What if we don't want, need, or have a tree-like topology in our environment? What if all we want is to have a primary and secondary path to everything within our network, allowing us to create a ring topology? Oftentimes, simply having a primary and backup path from any source to any destination is sufficient. If we're able to configure our network topology in such a way, this greatly simplifies the creation of a loop-free topology. So, let's take a look. In such a case, the complexities of determining a loop-free topology are largely eliminated, allowing us to use a much faster and simpler protocol, Ethernet Ring Protection Switching, or ERPS. ERPS is defined in ITUT G.8032 and provides very reliable and very fast convergence in a ring topology. The target convergence time from a failure is 50 milliseconds. To put that convergence speed into perspective, that's fast enough for a phone call to not be noticeably interrupted, and is 1,000 times faster than Spanning Tree Protocol. Pretty impressive, right? ERPS, of course, only works with ring topologies. Trees are not supported. However, it's possible to create complex ring topologies with main rings and subrings, though those more complex topologies are not covered in the JNCIS ENT. I'm sure you're wondering, how does ERPS provide such fast failover? Well, let's take a look. As we can tell in our topology here, since we have a ring, if a single link is blocked, we now have a loop-free topology. This blocked link in ERPS is called the Ring Protection Link, or RPL. The node which controls the blocking of the RPL is called the RPL owner. During normal operation, when there are no failures detected in the topology, the RPL is blocked by the RPL owner. In a failure scenario, the RPL owner unblocks the RPL to restore continuity to the network, and when the failure is repaired, the RPL is blocked again to ensure a loop-free topology is maintained. The RPL owner is notified of failures by receiving a Ring Automatic Protection Switching message, or RAPS messages. All nodes in the ring participate in RAPS messages, as we'll see in a later slide in this lesson. I mentioned a bit earlier that the ERPS protocol is much simpler than Spanning Tree. So let's take a look at the messages that switches participate in ERPS exchange. There are only 7 fields in the wraps frame, and only 4 of them are actually used. First, we have the request or state field. This field is used to indicate whether there is a failure detected in the ring or not. When set to all zeros, this is known as the no request message, indicating no failure is detected in the ring. When set to 1011, it indicates there is a failure detected in the ring. The next field is set to all zeros and is reserved for future use. The next 2 fields, though, are 1-bit flags, the RPL blocked flag and do not flush flag. The RPL blocked flag is only signaled by the RPL owner. No other switches participating in ERPS may set or unset this flag. Setting to a 1 indicates the RPL is currently blocked, and setting to a 0 indicates it is currently unblocked. The do not flush flag indicates to the receiving switches whether they should flush their MAC address tables or not. A 1 in this flag indicates the other switches should not flush their forwarding tables. A 0 in this flag indicates participating switches should flush their MAC address tables. This is used to allow participating switches to quickly relearn which ring port MAC addresses are accessible over in the event of a failure detection or restoration. The next field, status reserved, is a reserved field and set to all zeros. The last used field is the node ID field, which contains the MAC address of the node which is originating the wraps message, since all nodes participating in ERPS can send wraps messages. The last field is also reserved and always set to all zeros in practice. Now that we have a good sense of how the wraps messages are structured, let's review how switches use these messages in ERPS operations. During normal operation, the RPL owner is the only node sending wraps messages. It will send a wraps message every 5 seconds by default on Junos devices and sends them out all interfaces participating in ERPS. The RPL in normal operation will be blocked. So the RPL blocked flag will be set to 1. And being that there's no failure detected, the state field is set to all zeros. Something contrary to intuition is the do not flush flag is set to 0, indicating participating switches should flush their MAC tables. The participating switches only flush their MAC address tables the first time this message is received, and do not continue flushing on subsequent messages. In this normal operation steady state, we have a loop-free topology. The RPL is blocking data traffic, although wraps messages are still sent out the RPL port, and the topology is stable. Now, let's see what happens when a failure is detected. When a failure occurs and is detected, the node or nodes which detect the failure send a wraps message with these values set. The state field is set to indicate a failure is detected with 1011, and the do not flush indicates the switches should flush their MAC tables. Since this is a new wraps message being received, the participating switches do indeed flush their forwarding tables the first time this new message is received, though not on subsequent messages. The node which detected the failure will continue to originate these RAPS messages every 5 seconds until the failure is fixed. The node that detected the failure will place the port connected to the failed link in a blocking state to ensure a loop is not formed when the link is repaired. When the RPL owner receives the RAPS message indicating a failure is detected, the RPL will be unblocked to restore continuity to the rest of the ring, and the RPL owner will cease sending RAPS messages. This state of the ERPS ring is called the protection state, where the RPL is unblocked due to a detected failure. Now, let's review the process the nodes follow when the link is repaired so the ring may return to the normal operation state. When the node that detected the failed link sees that the link is now restored, it will continue to block the port connected to that link and will adjust its RAPS message. The new message sent will indicate that there's no failure detected by setting the request state field to all zeros once again. The do not flush flag is set to 1, so the switches receiving the new RAPS message do not flush their MAC tables quite yet. When the node sees that the failed link is restored, it starts counting down a wait to restore timer, or WTR timer. This WTR timer should be consistent across all nodes participating in ERPS. When the RPL owner receives this RAPS message that the link is restored, it will also begin counting down the WTR timer. Once the WTR timer expires, the RPL owner will block the RPL once again and begin sending RAPS messages again with the same field configurations as in the normal operation. The nodes that detected the failure and subsequent restoration will continue to originate RAPS messages until the RAPS message is seen from the RPL owner, indicating the RPL is once again blocked. Once the RAPS message is received from the RPL owner, the node that originally detected the failure will unblock the port that the failure was detected on to restore continuity to the network. Great. So now that we have a good understanding of how ERPS works, let's review how to configure ERPS on our Juno switches. First, we'll start with the RPL owner. First, on the right, we see the interface and VLAN configurations. The interfaces are configured like any other trunk interface, with the interface mode set to trunk and the VLAN members added. Note that in the VLANs configuration, we not only have our two data VLANs, but also an RPS control VLAN. A control VLAN is needed to segregate the RAPS messages onto their own VLAN in the ERPS network. GE000 and GE001 are the ring ports on the RPL owner, and we see the ERPS configurations on the left. ERPS is configured in the Edit Protocols Protection Group Ethernet ring configuration hierarchy. First, we have the name of the ring configured here as CL-ring-01. We see that this node is configured as the RPL owner with the Ring Protection Link Owner configuration command. ERPS has a concept of east and west ports to help network administrators keep track of which direction around the ring that each port faces. The east and west configuration is purely cosmetic, though, so it won't interfere with the operation if these are mixed up in configurations on other nodes in the ring. The RPL is configured with the Ring Protection Link End configuration command under the east or west interface. At the bottom, we have our VLAN configurations for the ring. The control VLAN command specifies the name of the VLAN to be used for sending the wraps messages. Then, the data VLANs, which this ring carries, and which are blocked by the RPL, are defined in the data channel configuration shown here. And that's it. So, it's a slightly more complicated configuration than Spanning Tree Protocol, though much faster and more consistent operation. So this was the RPL owner configuration. Let's take a brief look at how the configuration differs on another participating node in the ring. We see here that the interface and VLAN configurations on the right are identical to that on the RPL owner. The only differences in the Ethernet ring configuration on the left is the omission of the ring protection link owner and ring protection link end commands. Otherwise, the configuration is identical, and the east and west interfaces would be replaced with the correct interface names for this switch. It should be noted that multiple ERPS rings may be configured on a single switch, potentially creating complex ring topologies. Now, let's see what commands we use to monitor the state of ERPS. The Show Protection Group Ethernet Ring Interface command will show the status of each interface participating in ERPS. In this example, we're looking at the RPL owner, where GE000 is configured as the RPL. In the example output, from the left, we have the name of the interface, then the forwarding state. This may be in a discarding state on a participating node if a failure was detected or recently restored. The RPL end column indicates if the interface is configured as an RPL. The signal failure column indicates if a failure has been detected on this interface. And finally, the admin state column gives the administrative configuration state of the interface. I appreciate you sticking with me in this lesson while we reviewed the theory, operations, and configuration of Ethernet ring protection switching. I hope that this lesson has been informative for you, and I would like to thank you for viewing.